Hello. No, I'm not going to play the guitar today for you. I wish I could play this beautiful instrument, but I can only use it as a physics teacher to show you about frequency and its relationship to the length of each string. So I'm just going to demonstrate using the second one, the frequency that we hear with full length and shorter lengths. If you're a musician, I apologize for holding the instrument wrong or playing it wrong. I'm sorry, but my intentions are good. So let's go. This is the second string with full length. I'm now gonna reduce the length to around half. And that's what I hear at shorter lengths. So this is probably not new to you, but let's try to understand how this works. So in this lesson, we're going to learn about standing waves. Before I explain the difference between standing and traveling waves to you, I will show you this video which was taken at a laboratory with a wave tank. You're going to see waves approaching from this side. They're traveling waves, but we know that waves would reflect from this end. So there's going to be then a wave that is approaching towards us and the wave that is moving away from us in the same medium. Those two waves will be interfering with each other. And let's see what that does. The waves are coming in. And now it started reflecting. And there's our standing wave. We describe the differences between standing waves and traveling waves under three categories: amplitude, phase difference, and the energy propagation through the medium. So let's watch what happens on a standing wave. The blue and the red waves are two waves moving in the opposite direction, and the black wave shows the standing wave formed as a result of their superposition. In terms of the amplitude, all particles of the medium on a traveling wave have the same amplitude, but the amplitude varies with distance on a standing wave. To explain this, I'd like you to watch each of the particles that are within half of a wavelength. The particle that is here in the medium has maximum amplitude. The particle that is here closer to a node has a much smaller amplitude. That red particle has 0 amplitude. So they're obviously moving at different average speeds, and they all have different amplitudes. But in a traveling wave, all particles have the same amplitude. They all have the same maximum displacement from their equilibrium positions. The second difference is in terms of energy transfer. Energy is seen to be traveling across the medium through a traveling wave, but that's not the case with a standing wave. When we look at a standing wave, we do not observe energy being transmitted across the medium, unlike a traveling wave. The third difference is in terms of the phase difference between oscillational particles of the medium. Now, when I play the simulation, I'm asking you to look at all the particles that are within half a wave. Do you see that they all reach their maximum displacement at the same time? They all pass through equilibrium position at the same time. What does that say about their phase relationship? Every particle on a standing wave within half a wavelength are in phase. However, in a traveling wave, particles are not in phase. They reach the same amplitude but at different times. So, I've prepared some videos for you to show how standing waves can be formed with slinkies first. I have a slinky here that I'm holding from this end, and the other end is fixed. Speaking of a fixed end, let's remember how a wave reflects from a fixed end. From the reflection lesson, you should remember that when a wave reflects from a fixed end, it goes through a pi phase change, which means it will be inverted when it reflects. Now, we will watch what happens when the wave continuously interferes with itself on the Slinky. Now, I'm going to pause right there. I call this the second harmonic because you can see there's one point that is the maximum amplitude and another point that has a maximum amplitude. And there's a point in the middle here. Watch what happens at that point. We call that point the node, and the points that have maximum amplitude, antinodes. This is what the third harmonic would look like. There are 3 antinodes. This is what the fourth harmonic would look like. From the reflection lesson, let's remember what it means to go through a free end reflection. When a wave reflects from a free end, it goes through no phase change, meaning that it will not be inverted and it can reflect from the same side as it reached that end, and it can interfere with itself without being inverted. Now, you're going to see me turning this, but this is a model for you to be able to see how standing waves look like on one end fixed and one end free strings. This is what one possible case looks like. Please watch that at my fixed end, there is a node which is not oscillating. But watch what happens at the free end. First, we're going to look at superposition with reflection from fixed end. Before I play, please remember, when there's fixed end reflection, the wave goes through a pi phase change, which means the incident wave will interfere with the reflected wave, which has a pi phase difference, which means at that fixed end, the displacements of the original wave and the reflected wave will always add up to 0 as shown. Which is why at a fixed end there is always going to be a node formed, whereas from a free end there is no phase change, so the original wave and the reflected wave are in phase, so adding their displacements means having an amplitude at that point. Let's talk about the harmonics. When both ends are fixed. Now, in this simulation, the blue line is going to show us the incident wave and the orange will show us the reflected wave. Always focus on the green. The blue and the orange are there to help you see how the displacements add up. So at the node points, you will see that the blue and the orange line always have a 0 total displacement. And at an antinode, for the second harmonic we're looking at now, the displacements of the blue and the red of the orange, the displacement of the blue and the orange always add up to cause a maximum. Let's see how this looks when both ends are free. The incident wave, the orange reflected wave, and because it's free, you see that they are in phase, causing an amplitude at the ends. This is an image to show you what this would look like on a longitudinal wave. The next harmonic and how it would look on an open-ended air column, and the third harmonic on a string. So what happens when one end is fixed? The blue line, adding the orange wave as its reflection. Now this end is a fixed end and the other end is a free end. So we have to start with a node and end with an antinode. This is how it would look for a sound wave. You see there's always a maximum oscillation on this end, and the node end is not oscillating. This is called third harmonic. And the fifth harmonic, and the fifth harmonic with sound view. You might find it hard to imagine how sound reflects from an open end and forms the standing waves within the pipe. Now I'm going to try to show you how this works using tuning forks and an open pipe. Our goal now is to explain all this mathematically. How is the frequency, the length of the tube, and the shape of the tube all related, and how do the first and second and third harmonics form on strings or open air pipes? Our first case is a string with two fixed ends. Things to remember: as long as the wave is traveling on the same string, it's moving with the same speed. And the wave equation, which is V equals frequency times the wavelength. So, this is where the incident and the reflected waves interfere destructively. And this is where they always interfere constructively. The first thing we need to identify is the wavelength and its relationship to the length of the rope that we are using. Do you see that this is half a wavelength? So the length of this rope is half lambda. That means I can write lambda as 2L, and using the wave equation, I can write an expression for the frequency of this standing wave occurring, V divided by the wavelength. Substituting 2L for the wavelength, I have V over 2L expression. Let's move on. This is how the second harmonic would look. So to call this for second harmonic, we have, again, since the two ends are fixed, we have a node at the start, a node at the end, and add a node in the middle. What that does is changing the wavelength. So this is happening at a different frequency. Our goals are finding the relationship between frequency, the length of the rope, and the speed, but we also want to relate at which frequencies these patterns take place. So I'm going to look for a way to relate this to the first case. Can you see that this is now one wavelength? So now I can write wavelength equals L, and the second frequency that I'm relating to this new case, which I call the second harmonic, the V, which must be the same because the wave is moving on the same string, divided by lambda, which is now 1L. Moving on to the third harmonic, starting with an N, ending with an N. Let's add one more N in the middle. And now can you see that this is 1.5 wavelengths within the same L? So I can write L equals 1.5 lambda. That allows me to come up with lambda being equal to 2/3 of L. When I substitute 2/3 L in my wave equation, I get the new frequency as 3V over 2L. Now, if I call F1 1F, which is the value of this ratio, V over 2L, how many F would be V over L? It would be 2F. Do the same for this one. How many F is F3 equivalent to? Answer is 3F. And there's our pattern. For strings fixed at two ends, if the first harmonic takes place at F, the second harmonic takes place at twice that value, and the third harmonic takes place 3 times that value. We also call the first harmonic the fundamental frequency. Let's see how the story changes when there are two open ends. Our first diagram. When there's an open end, we learned that there must be an antinode. Now we have two open ends, so we have to start with an antinode and end with another antinode, which means going from one antinode to the closest antinode would be this shape. Do you see that this again is half a wavelength? I do the same thing as before. I write this wavelength in terms of the length of my air column. So F1 expression, I get V over 2L because 2L is the wavelength. The second harmonic, A and another A, you have to start and end with an antinode because we have two open ends, add one in the middle. So now you can see that this is exactly one wavelength. So now I have lambda equals L, which means this frequency equals V over 1L. You should be looking for the similarity with the previous case at this point. Before we move on, let's look at the third harmonic. I have an antinode to start with, I have an antinode to end with, and I have another antinode between them. So now, since this is one wavelength and that is half a wavelength, the total length has become 3/2 of lambda, which means lambda is 2/3 of L. Substituting it for lambda in my wave equation, I get an expression for this third harmonic frequency as 3V over 2L. Take a moment to relate F1, F2, and F3, and you will see that they follow exactly the same pattern as when the two ends were fixed. So, mathematically, the two ends open and the two ends closed cases work exactly the same way. If the first harmonic, in other words, fundamental frequency, takes place at a frequency F, let's say 50 Hz, next harmonic will be observed at 100 Hz, and the third harmonic will happen at 150 Hz. Can you guess at what frequency we will find the fourth harmonic? If you're saying 200 Hz, you're right. Finally, let's see how it works when one end is closed and one end is open. The situation has changed because at the start, where we have a closed end, there must be a node. At the open end, we have to have an antinode. Going from a node to an antinode, you can see that is actually quarter of a wavelength, which means wavelength is equal to 4 times the length of this air column. So using the wave equation, substituting 4L for lambda, I now get V over 4L for my fundamental frequency. In other words, first harmonic frequency for an air column with one closed and one open end. To have one end closed, starting with a node, and one end open, ending with an antinode, this would be the next shape that is possible. If you split this into 3 parts, you can see that this is a quarter of a wavelength, another quarter, and another quarter. So this situation is possible when length of this air column is 3/4 of a wavelength. So this wavelength is 4/3 of our length, which means that expression for the next harmonic frequency. Now you must have already realized that I'm not calling this F2 anymore. I'm calling this F3 for a reason I will explain in a minute. The next case, going from N to an A, you can see this is one wavelength and a quarter. So this length is 1 plus a quarter wavelength, which means the wavelength is 4/5 of this length. When I come up with an expression for the frequency of this situation, I found 5V over 4L. If the fundamental frequency takes place at 50 Hz, which is the result of V over 4L calculation. 3V over 4L is 3 times that expression, 150, 3 times the fundamental. The next one will occur at 5 times the fundamental. If V over 4L is the fundamental, this is 5 times that. So the next time when it will happen at 5F, which would be 250 Hertz. When the medium has 2 open or 2 closed ends, the harmonics can be labeled first, second, third, fourth, etc. Only when one end is closed and one end is open, we label the first harmonic as the fundamental frequency, but the next is the third harmonic, and then the next is fifth, and that's how the pattern goes for this particular case. Here's a summary for you to make notes. One thing I am definitely going to ask you to do is to make these drawings into your books. It takes a lot of practice to be able to produce these on your paper. That leaves us with homework. I will scroll through the pages, solutions of these questions on my next video. Thank you.